Hello, everyone. Sorry for the technical difficulties. My name is Noushin Azami. Today I'm going to talk about this project that we started working on a few months back. It's a new implementation of homomorphic encryption using CAPI, Apache Arrow, and Fletcher. So feel free to ask any questions during this presentation. I'll take any questions. And a little about me, that I'm starting my PhD in computer science at Texas State University in a week. I graduated a week ago from my master's in electrical engineering, again at Texas State. I finished my bachelor's in computer engineering in Iran, and you can find all sorts of information about me on my LinkedIn page. So a list of collaborators for this project is my advisor, Dr. Apan Qasim at Texas State, is Dr. Peter Hofsty here at IBM, and Jeffrey Kellington, which probably most of you know as JT at IBM. A little bit of introduction. We know there's more data every day, and so data servers need more processing power. So we know that a lot of operation and processing on data is not being done locally and being done on servers. So there are people, clients, who are giving out their data to the servers, and they need to trust in the system. And there is a need for some kind of security that they can trust in their servers having their data. And that a solution in that area would be homomorphic encryption. So homomorphic encryption is basically the ability to perform operations on encrypted data without having the key to decrypt it, which is like a client. There is a client holding an input X, and she wants the value of fx from a server, but doesn't want the server to know what x is. An example in cloud computing would be a driver wanting to find directions without giving out her location. And the location would be the input that is important for the client not to give out to the server. There have been solutions proposed over the past 40 years under different names, like computing unencrypted data, privacy homomorphism, and homomorphic encryption. So here is the simplest way to talk about the main idea of homomorphic encryption. There is a function f. In that example, that would be finding the directions to somewhere. And there is the input x. And in the past example, that will be the driver's location. And there is a ciphertext, which we'll call C from now on. It is an encryption of the driver's location. It's an encryption of your input. So if you look at this table, you'll see, you'll get some kind of an idea about homomorphic encryption. There's a client side and a server side. Again, the client knows the input x, knows what f is, the function, and doesn't want to reveal x, and doesn't want to know the details of f, but wants to know what fx is, which is our output output of function f, given that their input is x. There's a server side that does not know what x is. There is no input given to it, but then knows a encryption of that x, which we call C, and knows in details of f, and does not want to reveal the details of f to the client. And there is an important concept called evaluation procedure, which is a procedure that giving the input of a ciphertext encrypting x and a description of function f gives out an evaluated ciphertext that can be decrypted later to fx by anyone who has the key to decrypt it, which is not the client. The client doesn't, which is not the server. The server does not have the key to decrypt this. There is the concept of compactness, which means that the complexity of decrypting an evaluated function does not depend on the function. And with that comes the concept of compact fully homomorphic encryption, which is a compact scheme that can evaluate all functions. There are different levels in homomorphic encryption. There are homomorphic encryption schemes that can evaluate some functions. We're going to look into that later. But for a scheme to have the ability to evaluate all functions given to it makes it a fully homomorphic encryption, fully homomorphic scheme. This is not, sorry.
Oh, good.
Sorry. Do you have any questions still out? Any ideas? Nothing?
I don't know. At this point, we don't have the. So I'm afraid that's now going to have lost it again. But at least I still have my. Oh, did it come back? Idea why it stops like that. But I guess this is where you were, right?
Yes, thank you. Let me see. Okay, we're going to talk about Gentrys Blueprint that has been proposed in 2009, which is basically somehow recently, and before that, there was no blueprint that can construct a fully homomorphic scheme, but Gentrys came up with a blueprint to do so. So I'm going to explain this. There's a little bit of math in that. I'm sorry in advance for it. So in Gentrys Blueprint, there is a secret key. We'll call it P, which is a large odd number. And how the scheme works is the encryption of a bit B is an integer whose residue model of P has the same parity as bit B. Okay, that sounds a little complex, I know, but so there is our input X that we called before X. We'll call it B here, which is a bit that can be 0 or 1. There's a ciphertext, CX, which this is basically our scheme. This is how we're encrypting our data. And this sends here equal to this formula, PQ plus 2R plus B. Remember, our P was our secret key. Q and R are random, and we know that the value of R is a lot less than P. So how it works is, okay, so we saw how the encryption works. Now, how the decryption works is that the client having the key P can do this formula here, having the ciphertext, mod P mod 2 gives it the bit B. This is how the decryption works. And it's important to notice that only the client has the secret key, not the server. Again, a graph to kind of show you how it works. There is the client side and the server side. Client giving, this is in Gentrys Blueprint, where R, Q are produced randomly. There's the B, which is our input. There's the P, which is the secret key, and there's the function F. We assume here we want to do an addition of 2 integers. And given out the scheme to the client, it will give out the ciphertext and the function to the server. The server evaluates the function and gives it back to the client and client having the secret key, which is P, can decrypt this to the function FB. All right. Okay. So let's look at one evaluation function. There is the client wants to know what FB is, which is B1 plus B2, but doesn't want the server to know what B1 and B2 are. So it will give out C1 and C2 to the server. So giving the scheme, we can encrypt our B1 to C1 like QP plus 2R plus B. That's what we saw earlier. So we encrypt both these inputs and we produce C1 and C2. What is important here is that the function of addition gives out the same format as our encryption before. So it can be decrypted to the right values. But it is important also to notice that R1 and R2, the small the small values that we have seen before, need to be small enough so that the noise, actually they have to be smaller than p over 2 so that the noise doesn't ruin the function. So if they're small enough, they're still decryptable to the right value. And generally speaking, just this function can be done on addition, on multiplication, and generally speaking to all low-degree polynomials on ciphertext. Given out that the noise is small enough, it would be decryptable to the right value. So here's an example to see it in integers. P was our secret key, which was a large odd number as 51. There are inputs B1 and B2. We give them 0 and 1. What the client wants to know is 0 plus 1. So the server should give it a evaluated ciphertext that can later be decrypted to 1. We all agree on that, right? Okay, great. I just want to know that you're following this. So we produce our Q and R random numbers, and we encrypt our B1 and B2 and send them to the server. So B1 plus B2 equals 1 is what we are hoping to get from this. So let's see what the server does. So our encrypted values are going to be 463 and 364. These are the values that the server is getting, not 1 and 0. So the server knows to add these through, so it gives out 827 and gives it back to the client. So now what the client has to do is to decrypt it to the value it wants to. And if the client is still going to use the key 51 to do so. So let's see, 827 mod 51 mod 2 gives out 1, which is the exact result that we were hoping for. Shows that the scheme works for addition function evaluation. And trust me on this, it's going to work on multiplication and any polynomial also. But, well, this scheme is not compact because the bit size of the ciphertext grows with the degree of the polynomial. And their noise magnitude grows with the degree. And at some point, it's going to fail. And that will be when the noise hits p over 2. And so Gentrys solved this by bootstrapping, which is, again, another complex concept, but I'm just going to give you a sentence describing it. He realized that any homomorphic scheme which is capable of evaluating its own decryption and a NAND gate can be turned into a fully homomorphic scheme. I'm not going to get into how it's done, but I'm just telling you it's a complex and it's going to be power hungry. It's going to be very slow because there are a lot of operations that has to be done. With that, we're going to talk about how we can improve this. Fully homomorphic encryption is not right now something we can do on real-time processing, and because it's slow and it's not fast enough. So we can make it faster using hardware acceleration, and which is basically offloading parts of your system that are computationally intensive to a hardware. In this case, a good hardware would be an FPGA because it can be reprogrammed and because it offers high degrees of parallelism. There has been work done on boosting the speed of homomorphic encryption schemes with FPGAs. There has been FPGA coprocessors, FPGA-based high-performance parallel architecture. So in the second one in specific, they optimized their design, and they proposed a hardware accelerator for homomorphic encryption scheme that they were working on, but they were faced with a large data transfer overhead. And in some cases, even the function evaluation of multiplication, the hardware side could do a job of a lot faster of processing that multiplication, but still the overall timing didn't change at all because there was a lot of data overhead produced because data has to be sent back and forth between platforms. So they came up with solutions for that. They tried assigning more memory to the FPGA so that the data can be processed locally. And they tried finding the most efficient data set size so that having to send data back and forth doesn't produce that much of an overhead. But we know that there are better ways to fix those. So what we came up with was by using CAPI and Apache Arrow. CAPI giving the OpenCAPI, a CAPI giving the FPGA a coherent memory access, and Apache Arrow being being in in-memory tabular format. They both reduce data copy overhead. And so here is some information on OpenCAPI, but this is actually for CAPI Power 8, I guess. And so it creates virtual memory for FPGA, giving the FPGA coherent access to the memory and eliminating the need to copy data back and forth to send it from CPU to the FPGA. And Apache Arrow is a cross-language development platform for in-memory data. There are many languages that support it. C, C++, the list goes on. This is only some of the languages. And so Apache Arrow, by eliminating the need for serialization, can reduce the data overhead transfer when data needs to be sent back and forth between platforms. In our case, from CPU to FPGA and from FPGA to CPU. And there's Fletcher, which is a framework that integrates FPGA accelerators with Apache Arrow. I'm not going to go into detail about this because the folks that created Fletcher are here and going to talk about this after this. And all I say is that it's open source and you can find information on it in this website on GitHub. So where we are now with this project is that we are testing and learning to run simple codes using Fletcher. We're kind of following what the folks at Delft are doing. And we're researching on homomorphic encryption, finding the best schemes that can benefit most from this kind of implementation. And so we're kind of at a starting phase with this project, so any ideas or recommendation that you have is very well accepted. Thank you so much.
We have time for questions.
Question? Okay.
So thanks for the talk, very interesting. So I was wondering, you mentioned that a bunch of operations work well with homomorphic encryption, but there are also a few that don't work very well, specific operations.
Specific functions, you mean?
Yeah.
Okay, so the fully homomorphic, so we saw how the function could be decrypted to the right value, right, in the addition with that scheme. So that scheme provides the ability for that function to be decrypted to the right value. But not all functions can be decrypted to the right value because there is noise created and maybe the scheme is not mathematically correct. So we have to come up with new schemes that can make this happen for all functions, not just like low-degree polynomials. Do you have a question? Yeah. I think that's the machine that we have. Yes, well, the thing is we're not really platform dependent at this point. So what we're doing is trying to figure out our side of this, and then we'll figure out which machine we're going to upload this on. Probably, I think we talked to JT about this. They're going to give us the OpenCAPI machine so that we can work on that one. Yeah. Was there any other questions? Thank you.